seminar, and today Masud is graduate student is in the RUDN University. So Masud will tell us about epidemic models with time delay. So please, Masud, you can start your presentation.
Okay, thank you, Professor Volker, for this introduction, and also I would like to thank Professor Anastasia Mazukhina for her help in the technical issues, although I forgot some of the advices about that. So today I will talk about an epidemic model with time delays determined by infectivity period and disease duration. And actually this recently finished work is also a joint work with Professor Vitaly Volpert, Professor Malay Banerjee, and Samiran Ghosh. Here are the contents of this talk. First, I will give a brief biological introduction. Then I will I will show how we formulated the model with distributed recovery and death rates. And then we will reduce this model to the conventional ODE model. After that, we will continue and we will reduce it also to the delay model, and then we will find some epidemic characteristics of the epidemic progression through the delay model. Then we will show some numerical simulation where we investigate the Omicron variant through our delay model and also through our or through the ODE model. And we will end this talk by a discussion where we present some conclusions and further perspective about this work. So actually, when a disease spreads in a population, it usually divides this population into non-intersecting compartments. And in our scenario, we have 5 compartments. The first one contains individuals who are healthy, but they are able to contract the infection once in contact with some infectious individual. We call this compartment the susceptible compartment, and we denote it by letter S. Then we have the individuals for whom viral infection develops in the organism, but they don't yet transmit the disease to other individuals. We call them the exposed individuals, and we denote this compartment by letter E. Then we have the class of individuals who have contracted the disease and they are now sick with this disease. And we call them the infectious individuals, and we denote their compartment by letter I. Next, we have the group of people who have recovered from the disease and become immune to it. They are no longer able to contract or to transmit the disease anymore. We call them the recovered individuals, and we denote this compartment by letter R. And finally, we have the group of individuals who have died because of this disease, and we denote their compartment by letter D. Actually, when a susceptible individual enters into a contact with an infectious individuals, then he becomes exposed individuals, which mean infected but not infectious yet. with some certain probability. And then he moves from the susceptible class to the exposed class. So, the number of newly exposed individuals at time t appears at the rate here beta over n, which is proportional to the product of the number of susceptible individuals and the number of infectious individuals at time t. And actually, this transition from the exposed, I'm sorry, then they become infectious first. They become infectious now, and which means that they are now able to infect other individuals and transmit the disease to the healthy people. And this transition from exposed compartment to the infectious compartment corresponds to the period which is called the infectivity period. And we can define this period to be the time interval between when a person is infected by a pathogen and to when they become infectious. On the other hand, the appearance of the symptoms and signs on the individuals corresponds to the incubation period, which can be defined as the time elapses between exposure to a pathogen and to when individuals show symptoms and signs for the first time. And actually, the infectivity period is different than the incubation period, although sometimes their duration can be quite close, but usually the duration of infectivity period is less than the duration of the incubation period. For example, if we take the case of influenza, we can notice that the individuals become infectious one day before they show visible flu signs. And also we can tell that emergence and severity of the symptoms corresponds to several factors, including the virus virulence and individual immune response. And the transition from the infectious compartment to either the recovered or dead corresponds to another period, which is called the disease duration. And we can define this period as a time interval between when a person can first transmit an infection to other people to when they are no longer contagious. So after this brief biological introduction, I will start the derivation of the model with distributed recovery and death rates by introducing this class of newly exposed individuals at time t, which can be defined as the rate of the decrease of the number of susceptible individuals. And we assume that the total size of population n, which equals the sum of all of these 5 compartments at every time t, to be constant because we don't consider new births or new deaths and other demographic issues here. We will denote the infectivity period by tau 0, and then j of t minus tau 0 will represent the newly infectious people at time t, or we can also say they represent it represents the newly exposed individuals at time t minus tau 0. And we will define the rate of change of the exposed individuals at time t as subtracting the number of newly infectious individuals at time t from the number of newly exposed individuals at time t. Now, if we differentiate this equation, then we will obtain the following equation that represents the rate of change of the infectious individuals with respect to time. And if we integrate this equation from 0 to t, then we will obtain equation 2.4. And also we will we get the rate of change of the recovered population and rate of change of the dead population with respect to time given by these two integrals, where rho t minus eta and mu minus theta are the recovery and death rates at time t of the individuals who became infectious at time eta. And finally, here we have the model with distributed recovery and death rates, or we also can call it the integro-differential model, along with these initial conditions. And we can see that this model is quite complex, and it requires the knowledge of the distributed recovery and death rates here, which may not be available in the literature. So that's why we will try to reduce this model to a more simplified model, and we will consider two cases. The first case is the ODE conventional model, and the second case is the delay model. But before that, we have to mention that we have proved that the solution of the model with distributed recovery and delay rates and recovery and death rates exists, and this solution is unique and positive for all the positive values of time. Now we will begin the reduction to the ODE model by assuming the uniform distributions of recovery and death rates given by these two functions, where tau stands for the disease duration and eta stands for the time since being infectious. And now if we take the second equation of the previous model, of this model, and if we integrate both sides of this equation from 0 to t, then we obtain the number of exposed individuals at time t, which is equal to this integration. And this integration can be approximate as the number of newly infectious at time t multiplied by the infectivity rate tau 0. So therefore, equation B can be written as the following, where here lambda represents the reciprocal of the disease infectivity period. Now, if we substitute equations 2.8, these functions, if we substitute them in the last two equations of the distributed delay in these equations, then we obtain these two integrals. And so if we substitute all of them in equation 2.4, then we will obtain the following equation that represents the number of infectious population at time t. And then if we derive this equation with respect to time, and after doing some calculations, then we will reach this equation. And if we assume that the sum of rho 0 and mu 0 here is very small, then we finally obtain the following equations that represent the rate of change of the infectious population. And hence we finally get the SAIRT conventional model with these initial conditions. And if we talk a little bit about the dynamics that happen in this model, we can say that when a susceptible individual enters into a contact with an infectious individual, he becomes exposed, as I have said before. So this expression denotes the number of newly exposed individuals at time t who will leave the susceptible class to the exposed class, and then at a rate lambda, which is equals to the to 1 over the infectivity rate, and proportional to the number of exposed population, then this group of people will leave the exposed class to the infectious class. Then at rate equals to rho 0 plus mu 0 and proportional to the number of infectious individuals, this group of people will leave the infectious class. Part of them, which is rho 0 times IT, will recover from the disease and reside in the recovered class, and mu 0 IT will unfortunately die and reside in the dead class. Now I will continue to reduce the distributed model to our delay model by assuming that the individuals who were exposed at time t minus tau 0 minus tau will recover or die at time t with certain probabilities. And actually this assumption is consistent with the following choice of the functions rho and mu, where here rho 1 and mu 1 adds up to 1, and delta is the delta Dirac function. Then from the last two equations of the distributed model, we can easily find that the rate of change of the recovered and dead will be obtained by these two equations. Then if we integrate these two equations from 0 to t, then we will have the following integrals, which represents the number of recovered and dead at time t. Now, if we substitute them in equation 2.4, then we will obtain the number of infectious individuals at time t, which is equals to this integral. And we can easily find that this integral will be equal to this expression. So we have the number of infectious population at time t equals to subtracting the number of susceptible individuals at time t minus tau 0 from their number at time t minus tau 0 minus tau. And from that, we obtain the delay model with these initial conditions. And we can explain this model as follows. At every time t, a number of newly exposed individuals, j of t, will leave the susceptible class to the exposed class. And then when the infectivity period is passed, then this number of newly infectious individuals will leave the exposed class to the infectious class. And after that, when the disease duration is also over, then this number of individuals who are no longer contract the disease will leave the infectious compartment. Part of them determined by this expression will go to the recovered class, and the other part will go to the dead class. Now we will prove that the solution of the delay model is actually positive, exists, and is unique for every time, for any positive time. Here we have the first lemma that shows that any solution of the delay model is positive and is bounded also. And the second lemma proves that the pair omega d is a complete metric space with respect to the metric function that is given by this equality. And the set omega consists of all the elements T that satisfy these conditions. In lemma 3, we show that the map L from omega to omega given by this expression is well defined, and G of eta T is given by this following expression. Actually, lemma 4 proves that this map L is a contraction map on omega, and a contraction map is a map that satisfies this property, that if we take any two elements from omega, let's say, for example, x and y, then the distance d between Lx and Ly should be less than or equal to the distance between x and y multiplied by a positive constant. Let's, for example, name it k, but this k should be strictly less than 1. So maybe in a mathematical way, we can say that L is a contraction on the set omega if d of Lx, Ly is less than or equals to some constant k multiplied by dxy, where k is a positive but strictly less than 1. And here we have theorem 1 shows that the map L, the contraction map L, has a unique fixed point T belongs to omega and satisfies that L of T equals T. And theorem 2 actually complete the proof of the existence and uniqueness of the solution of the delay model. Now we will continue and find some characteristics, epidemic characteristics for the delay model. And first, we will start by the basic reproduction number, which can be denoted by R0, and it can be defined as the expected number of cases directly generated by one case in a population where all individuals are susceptible to the infection. Then from the equation 3.2, okay, I will go back to this equation. Okay, from this equation, if we derive both sides with respect to t, then we easily obtain this equation. And if we consider that at the beginning of the epidemic, that the number of susceptible population at time t minus tau 0 and t minus tau 0 minus tau will be equal to their number at time 0, And by substituting this in this equation, then we find that the rate of change of the infectious individuals at time t is given by this equation. Now, if we consider I of t to be I0 times e to the power nu t, where nu is the principal eigenvalue that represents the infection growth rate, then we obtain, of course, substituting it in this equation, then we obtain the following equation. And actually, this equation has a positive solution if and only if this expression is larger than 1, and this let us conclude that the basic reproduction number of the delay model is indeed equals to this expression, beta tau S0 over n. Now we will find the final size of the epidemic, and if we go back to the first equation of the delay model that represents the rate of change of the susceptibles, and after some calculation, and if we take the integral of both sides from 0 to infinity, then we will obtain this equation. Now, if we change the order of these two integrals and then doing some more calculations, then we finally obtain this equation 3.6, which represents the final size of susceptible class. Omega here equals to the final size of susceptible divided by their number at time 0, and R0 is the basic reproduction number. Also, if we integrate the last two equations of the delay model, these equations, if we integrate them from 0 to t and then take the limits when t approaches infinity, then we obtain the following equations. The first one represents the final size of the recovered population, and the second one represents the final size of the dead population. And if we plot this equation that represents the dependence of the final size of susceptibles on beta, which is included in the basic reproduction number, then we obtain the following graphs for different values of disease duration tau. And we can see that these graphs are monotonically decreasing with respect to the disease transmission rate beta. Now I will compare the growth rates for ODE model and with the growth rate with for the delay model. First, we will linearize the delay model about the disease-free equilibrium, and then we will obtain the following equation, where, as I have said, that here nu represents the principal eigenvalue, which represents the infection growth rate. And also a similar equation can be obtained for the ODE conventional model, which is given by this equation. Now, if we plot these two equations all together in one figure, then we will obtain the following figure. And we can see here the dependence of the growth rate in the delay model and in the ODE model on the disease transmission rate beta. Also from this figure, we can see that the growth rate for the delay model in magenta color is above the growth rate of the ODE model shown in cyan color, which means that the growth rate of the delay model is higher than the growth rate of the ODE model. And also we can notice that these two graphs are above the beta axis when beta is larger than 1 over tau, which corresponds to basic reproduction number larger than 1. And actually from this figure, we can observe the following results. First, as I have said, the delay model has a higher growth rate in comparison with the ODE model for the same basic reproduction number. And actually, this higher growth rate can lead to a higher peak of the epidemic, which achieved much earlier. And thus, to describe the epidemic progression in a more precise way, basic reproduction number is not sufficient. Rather, the estimate of the growth rate, which can give a better description of the epidemic progression. Next, we will have some numerical simulation where we will investigate the Omicron variant through the ODE model and the delay model. But first, we have to say that the Omicron variant has a shorter incubation period compared to the other variants, which can last from 1 day to 4 days. Also, its symptoms have been milder and have a shorter duration of 6 to 7 days. Moreover, recovery and death rates of the delay model are estimated easily from the clinical data, and the value of the disease transmission rate can be chosen to fit with the data. And finally, the parameters of the ODE model can be obtained from the corresponding parameters of the delay model using the following equations. So here in this figure, we have numerical simulations for the active cases of Omicron. And also we will try to investigate our delay model and ODE model for different countries for the time period from 15 of November 21 to 15 of May 22. So we have the following figures. We have the first one for active cases of Omicron in USA, the second one for France. Also, we have this figure for Germany and this one for Russia. Of course, for these values of parameters and these initial conditions, of course, for which can be differ for each country. And as we can see from every figure of these, then the delay model fits quite good with the real data with this set of values of the parameters, while the ODE model seems not to fit, or seems to be far away from fitting with this data for the same basic reproduction, for the same disease transmission rate and for the corresponding values of the other parameters. Also, we can notice that the maximum number of infectious achieved by the delay model is higher than the maximum number of infectious achieved through the ODE model. Also, the time to the maximum infectious in the delay model is much less than the time to the maximum infectious in the ODE model. And actually, this observation can be justified because of the fact that the ODE model overestimates the recovery and death rates, and this will lead to underestimation of the number of the active cases. And that's why the delay model seems to be more accurate in representing the real data. Also, we have these figures here, which show a numerical simulation for the ODE model for United States, and for the same time span from November 15 to 21 to May 15, 22. If we speak a little bit about this figure here, figure A, actually the red curve represents the delay model for beta equals 0.23, and tau 0 equals 2, tau equals 6, and the recovery rate for the delay model is here, and the death rate is 0.03. And the red curves here represents the infectious population for the ODE model, and we have many curves that corresponds to many values for the disease transmission rate beta within this interval. And we can notice that the variation of beta actually doesn't improve the description of the Omicron variant through the ODE model. Here in the figure B, we can show the ODE model, how the ODE model can represent the real data. And among these four curves, we can see that there is a curve, a red curve, that fits quite well with the real data. But to achieve this curve, we need to increase the disease transmission rate beta. For example, here for the delay model, we have beta equals 0.23. While here, for this red curve, we have beta equals 0.4. So we have increased beta, but also then we have to increase the recovery rate and death rate for the ODE model, because and if we did that, then we will obtain a disease duration to be less than the disease duration in case of the delay model. For example, here, the disease duration in case of delay model is six days, while when we increase rho 0 and mu 0, then we will have, for example, if we take their value here, 0.25, which corresponds to this curve that fit with the data, then it will be we know that rho 0 plus mu 0 is 1 over tau. Then from that we conclude that tau should be 4 days, while it is 6 days in case of the delay model, and this is in agreement with the clinical data. And also from this we can notice that in order for the ODE model to fit with the data, we need to increase disease transmission rate, and then we need to increase even more and more the recovery and death rates for the delay for the ODE model. Also, we can notice this from actually the relations between the parameters of the delay model and with those of the ODE model, because if we if we increase rho 0 and mu 0, then keeping rho 1 and mu 1 fixed, then we have to decrease the denominator tau, and that is why the disease duration in the ODE model always less than the disease duration in the delay model. And also, I have to mention that the basic reproduction number that can be obtained from this delay model is about 1.32, while the value of the basic reproduction number in case of the ODE model will be about 1.6. Finally, I will end this presentation by outlining some conclusions about our work. So first, we can notice that the epidemiological data model with distributed recovery and death rates is relatively complex, as I have mentioned and showed, and it requires the knowledge of distributed recovery and death rates, which may not be available in the literature. So that's why we derive from it two simplified models. The first one is the ODE model, where we assume that recovery and death rates are uniformly distributed. And the second one is the novel delay model, where these distributions are delta functions. Also, the delay model has a clear biological meaning, and it is determined by two main parameters, which are the infectivity period and the disease duration. And these two parameters can be easily obtained from the clinical data. Also, the epidemic progression is slower in the ODE conventional model than in the delay model and in the real data, because as we have seen, it overestimates the recoveries and deaths and underestimates the number of infectious individuals. Also, we have shown that the time to maximum infectious in the delay model is less than for the conventional ODE model. Moreover, the delay model has a higher growth rate in comparison with the ODE model, which can lead, and this higher growth rate can lead to a higher peak of the epidemic. Next, we saw that it's not sufficient to rely only on the basic reproduction number, rather on the estimation of the growth rate, which can give a better description of the epidemic progression. And also we can outline that this approach actually opens further applications to more complex multi-compartment models containing various groups of susceptible and or infected, and to immunoepidemic models with time varying recovery and death rates. And finally, it will be quite interesting to check the applicability of our proposed model to other transmissible diseases. Here we can see some of the references that we used in our work, and the presentation is over. And thank you for your presence here, and thank you for your attentions.
Yes, thank you, Masud, for this presentation. We have some time for questions and discussion, so I can start our discussion. Please show the model, the delay model.
Okay.
Yes, this one. Yes, yes, I would like to make some short comments about this model. First of all, you mentioned, but very shortly, and I'm not sure that it was really understood by our listeners, that this is a new model, and this is in fact the main interest of your work, of your presentation, that we derive here this new delay model, and we show that in some sense it works better than the classical SERIR model.
Yes.
So this is my first comment. The second comment is that, in fact, yes, it is a new model, but in our recent work, in fact, this year or last year, we derived a similar model without this exposed class, without equation 3.3. So it was a simplified model where we did not take into account these exposed individuals. Now, in this model, you do take into account exposed individuals, so it is a more complete model. So we can shortly compare these two models, with exposed and without exposed. Of course, you did not show in your talk the results about this previous model, but I will just mention two of these relations which you obtain. In particular, when you obtain the expression for the basic reproduction number.
Yes.
Could you show it, please? Yes. No.
3.5.
Yes, this one. So, yes, it's the bottom 3.5. So what is interesting is that this expression for the basic reproduction number is the same as for the model without exposed. So for some, I don't know, maybe it's clear. For me, it's not very obvious why, in fact, it appears that exposed individuals, this class of exposed individuals, does not change the expression for the basic reproduction number. And one more comment I would like to make about, show please the next slide.
Yeah.
Yes, this one, this equation 3.6. This is an important equation which appears in all models of this class, for the SIR model, for this SERIR model, and even for the immunological models which we study in some other works. And again, this is exactly the same equation. For the usual comportamental model, SIR, or without exposed and with exposed, and for the delay model, without exposed and with exposed, all the time we obtain the same equation, which, as you explained, make a link between the basic reproduction number and the final number of susceptible individuals. So it is exactly the same equation, but the basic reproduction number R0. Of course, if we compare the usual comportamental models and delay models, the expression for R0 is different, but the equation is exactly the same.
Yeah.
So these are several comments I would like to make. And to finish my comments, could you please show slide 18? This was a very, well, not that very interesting, but a little bit funny, because all the time you called green curves, you called red curves. So I thought that, do you see that as green or as red? This is so if you take the ODE model, I see it as a green curve. How do you see it, as green or as red? The ODE model, what color of the curve?
ODE green. ODE is green,
yes.
and delay model is the red curve. So
yes.
If I said
yeah,
because maybe it's a mistake. It's only a mistake.
Well, no, but okay, but I was just, but I thought that maybe it was related to some problem with your vision. Maybe it's kind of daltonism.
No,
No. Okay, sorry, just
Unfortunately not.
unfortunately. Fortunately not. Okay, so please, fortunately not.
Unfortunately.
Yes. Other questions or comments, please, from our audience.
I have one small question.
Yes, please, Anastasia.
Masud, could you please show one more time the slide with delayed model?
Okay.
Yes, thank you. Comment please once more. You have, do you have here two delays, tau 0 and tau?
Mm-hmm.
What each tau stands for?
Yes, tau 0 stands for the infectivity period, and tau stands for the disease duration.
Thank you. So in your delay model, you have two delays. Yes.
Yes, yes.
It's in fact, in this model, there are two delays. The next model, Masud studies now, there are three delays. One more delay. No, it's not just to increase the number of delays. This is not because you are laughing. It's not just the purpose to increase the number of delays. The purpose is to describe another important question. It's immunity waning. So recovered after some time, recovered lose their immunity and they return to the susceptible class. This is important.
Exactly.
So this is the third delay. This is the question Masud studies right now, and there are interesting results, and it will be the next the next seminar. Not in 1 week, not in 1 week, of course, sometime later, but the next in this.
Yes.
Okay.
I'm intrigued and waiting for the next talk.
Yes, it's interesting.
Thank you.
Well, other questions, please, from the listeners. Okay, I don't see other questions. So thank you again, Masud, for this presentation. It was well done. And thanks to all our listeners. We stop on that with our seminar today. Have a good day and bye for now.
Thank you very much.
Goodbye.
Thank you.